Module 1, Lecture C, Array Operations. By the end of this lecture, you will be able to apply elementwise arithmetic and universal functions to one-dimensional and multi-dimensional arrays, compute aggregations such as sum, mean, min, max, and axis-wise reductions on ndarrays, and perform basic linear algebra operations including dot products, matrix multiplication, and transposition using NumPy 2.2.6. Element-wise array operations. Vectorized array arithmetic. Vectorized array arithmetic lets you perform operations on whole arrays at once instead of using manual loops. When arrays have compatible shapes, you can add, subtract, multiply, or divide them, and the library automatically applies the operation to each pair of elements. This treats the array like a single mathematical object, such as a vector or matrix, and applies the operation to it as a whole. For example, you can adjust a month of daily temperature readings by a constant offset in one clear step without writing explicit loops. Vectorized arithmetic is especially powerful with multi-dimensional arrays because it lets you update many values at once. For example, you can adjust the brightness of every pixel in a grayscale image in a single operation, instead of looping through rows and columns. The same idea extends to three-dimensional arrays, such as stacks of images or time steps in a simulation, where you can transform all slices together. This is particularly useful in areas like climate modeling, where temperature or pressure values across multiple dimensions can be modified in one clear, efficient step. Vectorization lets universal functions operate on every element of an array at once and return a new array without writing explicit loops. When you apply trigonometric, exponential, or similar transformations, they automatically process all elements, which simplifies tasks like converting angles, modeling exponential growth, or adjusting sensor readings. By combining vectorized arithmetic with these functions, you can focus on the overall data transformation while the underlying library efficiently handles the element-wise details. Python code. Vectorized array arithmetic. This section shows how to adjust simple temperature data using vectorized array arithmetic. It compares doing these adjustments with slow manual loops to using fast built-in NumPy operations that work on whole arrays at once. Small arrays are used, so the results are easy to read and clearly show the difference between the two approaches. We begin by importing the NumPy library, which is essential for working efficiently with arrays and performing mathematical operations on whole datasets without writing explicit loops. This makes it easier and faster to handle large amounts of numerical data. We also import the time module, which lets us measure how long different operations take. Using these tools together allows us to compare the performance of different ways of manipulating arrays. We use a NumPy array to store daily Fahrenheit temperatures for a typical 5-day work week, such as afternoon readings in New York. The array holds 5 values, one for each day. By setting the data type to float, we make sure each temperature is stored as a floating point number. This allows us to perform precise arithmetic operations on the temperature data later on. We use NumPy to create a constant offset array that represents a sensor error where all readings are 2 degrees higher than the real temperature. This array contains the value 2 repeated 5 times and is stored as floating point numbers. By subtracting this offset array from the measured temperatures, we can easily correct the sensor readings and recover the actual values. To correct the temperature readings, we subtract the offset error from each original Fahrenheit value. Using NumPy, this subtraction is applied to the entire array at once. This means we do not need to write explicit loops in Python. Instead, we rely on NumPy's efficient array operations to handle all elements in a single step. To convert the corrected Fahrenheit temperatures to Celsius, we subtract 32 from each value and then multiply the result by 5 divided by 9. Using NumPy, this calculation is applied to every element in the array at once through vectorized, elementwise operations. This avoids writing explicit loops, making the code shorter and more efficient while producing the same Celsius results for each temperature. In this step, we apply the sine function to each value in the corrected Celsius temperature array using a NumPy universal function. This type of function automatically performs the sine calculation on every element without writing explicit loops. While taking the sine of temperature values is not physically meaningful, it clearly illustrates how element-wise transformations work in a vectorized way across an entire array. We begin by printing the original Fahrenheit temperatures stored in the weekly temperature array, so we have a clear baseline for comparison. Seeing these initial values makes it easier to notice how they change after we apply vectorized operations. Keeping the array small helps ensure that the printed output stays concise and easy to interpret. We correct the Fahrenheit temperature readings by subtracting a constant offset that represents the sensor error. Using NumPy, this subtraction is applied in a vectorized way to every value in the temperature array at once. The resulting corrected temperatures show how removing the offset changes the original readings. This illustrates how vectorized operations can efficiently adjust an entire dataset. We display the corrected Celsius temperatures that were calculated using vectorized arithmetic, meaning every value in the array was updated at the same time without writing explicit loops. To make the output easier to read, we then apply the NumPy rounding function to round each Celsius value to 2 decimal places before printing them. We compute the sine of the corrected Celsius temperatures using a NumPy universal function, which automatically applies the sine operation to each value in the array. The resulting sine values are then rounded to 3 decimal places for clarity. This example shows how NumPy universal functions efficiently perform element-wise operations on entire arrays in a concise way. To compare loop-based correction with vectorized correction, we first record the current time using the time module. This timestamp marks the start of the loop-based process and lets us measure how long the loop operations take to run. By knowing this duration, we can later compare the efficiency of manual loops against the performance of vectorized operations. We begin by creating an empty list called the corrected loop list, which will hold temperature values that have been manually adjusted. This approach is meant to imitate a non-vectorized method that beginners often use. As we loop through the original temperature data, we correct each value as needed and append it to this list one by one. In this way, the list gradually fills with the corrected temperature values. We go through each temperature in the weekly data one by one, subtract 2 degrees to correct the sensor error, and store the adjusted value in a new list. This process uses a manual loop to update each entry instead of applying a single operation to the whole array at once. It illustrates a basic, non-vectorized approach that beginners might use before learning NumPy's more efficient, vectorized methods for handling arrays. The code uses the time function from the time module to record the current time at the end of the loop-based temperature correction process. This timestamp marks when the loop finishes running. By comparing this end time with the previously recorded start time, we can determine how long the loop took to execute. In other words, it allows us to measure the total duration of the loop operation. We begin by recording the current time using the time module to mark the start of our vectorized operation. This initial timestamp lets us later measure how long the operation takes to run. By comparing this duration with the time taken by a manual loop, we can evaluate the efficiency of vectorized operations. In short, capturing the start time is the first step in timing and comparing different implementation approaches. We use NumPy to correct a week of temperature readings in Fahrenheit by applying a vectorized operation. Each value in the array is reduced by 2 degrees to fix a consistent sensor error that made all readings too high. This approach adjusts the entire set of temperatures at once and avoids writing an explicit loop. As a result, the correction is both simple to express and computationally efficient. The code records the current time using the time function to mark when the vectorized operation finishes. This timestamp is then compared with the start time to measure how long the vectorized approach takes. By comparing this duration with the time taken by a loop-based method, we can clearly see the performance benefits of using vectorized operations in NumPy. We display the list of temperatures that were adjusted using a manual loop, where 2 degrees are subtracted from each value in the original Fahrenheit data. This output shows the corrected temperatures and serves as a basis for comparison with the vectorized approach. The key idea is to contrast how the loop changes each value one by one with how the vectorized method applies the same correction to the entire array at once. This code prints an array of temperature values that have been corrected using vectorized operations. It demonstrates how NumPy can perform elementwise arithmetic efficiently and with simple syntax, instead of relying on manual loops. The output shows the adjusted temperatures after subtracting a constant offset from the original Fahrenheit readings. This line measures how long the loop-based correction takes to run. It does this by subtracting the start time from the end time of the loop. The result is then rounded to 6 decimal places to give a precise timing. This timing can then be compared directly with the performance of the vectorized version. The code measures how long a vectorized operation takes by subtracting the start time from the end time. It then uses a rounding function to limit this time difference to 6 decimal places, so the result is clear and easy to read. This timing helps demonstrate how efficient vectorized operations are compared to using manual loops. This script shows how vectorized operations in NumPy are much more efficient than traditional loops. It creates a set of Fahrenheit temperatures for a workweek, adds a constant offset to simulate a sensor error, then corrects the readings using vectorized subtraction. The corrected values are converted to Celsius, and a sine function is applied to these Celsius temperatures to demonstrate fast element-wise computation. The script prints the original and corrected temperatures in both units, along with the sine results, and compares the time needed for a manual loop-based correction versus the vectorized method. The outcome is that the vectorized approach is significantly faster, highlighting the performance advantages of using NumPy for array operations without explicit loops. Basic array arithmetic. In NumPy, basic array arithmetic lets you add, subtract, multiply, and divide entire arrays in one step. When two arrays have the same shape, NumPy applies the operation element by element, pairing each value in one array with the value in the same position in the other. This works for both one-dimensional data, like daily temperatures, and two-dimensional data, such as image matrices or sales tables. This element-wise behavior is the standard way NumPy handles array operations and is the foundation for more advanced numerical work. In NumPy, basic array arithmetic works element by element, so the arrays must have compatible shapes. This usually means they need the same dimensions and sizes, so each value lines up with a matching value, such as subtracting monthly costs from monthly sales to get profit for each store and month. When shapes do not match, NumPy either tries to adjust them using its broadcasting rules or raises an error if no sensible pairing is possible. Paying attention to shape compatibility helps you organize your data and ensures your computations are accurate. In NumPy, array arithmetic goes beyond addition and subtraction to include element-wise multiplication, division, and exponentiation, allowing you to transform entire datasets efficiently. You can, for example, convert distances from kilometers to miles by multiplying by a conversion factor, or find unit prices by dividing revenues by units sold. In scientific work, you might multiply concentrations by reaction rates or adjust sensor readings with calibration factors. Mastering these operations enables complex data transformations without manual, element-by-element processing. Python code. Basic array arithmetic. This section focuses on basic NumPy array arithmetic and how it works in a clear, simple way. It explains how to perform element-wise operations on both one-dimensional and two-dimensional arrays, so each position in one array is combined with the corresponding position in another. It also shows how array shapes must be compatible for these operations to work correctly. It illustrates how multiplying an array by a single number can be used for simple unit conversions, such as scaling all values in the array at once. In this script, we use the NumPy library, a key tool in Python for numerical computing. NumPy lets us work efficiently with arrays and provides many mathematical functions that operate on them. By using NumPy, we can perform arithmetic on arrays to manage data such as temperatures and sales figures in a structured and efficient way. We use one-dimensional arrays in NumPy to store the daily high temperatures in Fahrenheit for two different cities over a week. One array holds the temperatures for city A, and another holds the temperatures for city B for the same days. With these arrays, we can perform element-wise operations to directly compare and analyze the temperature patterns between the two cities. We can compare temperatures from city A and city B by doing element-wise operations on their arrays. First, we add the arrays element by element to get a new array where each value is the sum of both cities' temperatures for that day. Then, we subtract city B's array from city A's array element by element to get the temperature difference for each day. These simple operations let us combine and compare daily temperature data from the two cities efficiently. To convert temperatures from Fahrenheit to Celsius for each value in the city A array, first, subtract 32 from each temperature. This shifts the Fahrenheit scale, so it lines up with the Celsius 0 point. Then, multiply each result by 5 divided by 9. This changes the scale to match Celsius degrees and completes the conversion for every temperature in the array. We begin by setting up two-dimensional arrays to store weekly sales and costs for 3 stores and 3 products. One array records the sales amounts for each product in each store, and a second array records the corresponding costs. With this structure in place, we can easily perform element-wise calculations, such as finding profit for each product in each store by subtracting costs from sales. This organization makes later analysis straightforward and efficient. To find the profit for each store and product, we subtract the costs from the sales for each matching position in the arrays. This element-wise subtraction means each cost value is subtracted from the corresponding sales value, producing a new array of profits. Each entry in this profit array represents how much was earned for a specific item in a specific store. Using NumPy for this calculation lets us perform the operation efficiently for all stores and products in one step. We first combine the daily temperatures from City A and City B by adding their values element by element. Then we find the temperature differences by subtracting City B's values from City A's in the same way. After that, we convert City A's temperatures to Celsius and round each result to 1 decimal place for easier reading. Finally, we calculate the profit for each store and product by subtracting the cost values from the sales values in the corresponding positions of the two-dimensional arrays. This script uses NumPy to demonstrate basic array arithmetic with simple real-world examples. It first creates one-dimensional arrays for daily high temperatures in Fahrenheit for 2 cities, then adds and subtracts them element by element to find combined temperatures and differences. It also converts one city's temperatures from Fahrenheit to Celsius using scalar multiplication to show a basic unit conversion. The script then works with two-dimensional arrays representing weekly sales and costs for 3 stores, subtracting costs from sales to compute profit for each store and product. Overall, it illustrates how element-wise operations and scalar multiplication can be applied to arrays to perform practical calculations. Scalar broadcasting basics. Scalar broadcasting in NumPy lets you combine an array with a single value without manually matching their shapes. When you add or multiply an array by a scalar, NumPy conceptually expands the scalar to the array's shape and applies the operation to each element. This allows you to adjust all values in an array, such as a set of daily temperatures, by a single offset efficiently and without writing explicit loops. Scalar broadcasting in NumPy lets you apply a single value across entire multidimensional arrays, which is very useful in data analysis and scientific computing. For example, adding a scalar to a two-dimensional array of pixel intensities brightens a grayscale image uniformly. In the same way, multiplying a three-dimensional array of air quality measurements by a conversion factor adjusts all values at once. This makes it easy to perform simple, consistent transformations on complex data structures efficiently and with minimal code. Scalar broadcasting in NumPy lets you apply a single value across an entire array in a fast and efficient way. Because NumPy relies on optimized C code, this is much quicker than using Python loops, which is especially important for large datasets such as climate or financial data. It also makes your code clearer and closer to the underlying mathematical model, for example, when adjusting scores or converting units. By avoiding manual indexing, scalar broadcasting helps reduce errors and improves both readability and correctness. Python code, scalar broadcasting basics. This section explains scalar broadcasting in NumPy using simple arrays. It shows how a single scalar value can be applied automatically to every element of an array without writing explicit loops. You compare doing this operation manually with a loop to using NumPy's built-in broadcasting, which performs the same computation much faster. The goal is to highlight how broadcasting lets one scalar affect all array elements efficiently and concisely. In this lesson, we use the NumPy library, a key tool in Python for numerical computing with large, multi-dimensional arrays and matrices. NumPy provides efficient mathematical functions that operate on these arrays. We will focus on scalar broadcasting, which lets us apply an operation between a single value and an entire array. With broadcasting, the scalar is automatically applied to each element of the array without writing explicit loops. We create a one-dimensional NumPy array to store daily temperatures in Fahrenheit using the values 68, 70, 75, and 80. The array is set to use a floating point data type so that later calculations, such as adding or dividing these temperatures, are handled with good numerical precision. This ensures accurate results when performing arithmetic operations on the temperature data. We define a calibration offset with a value of 2.0 to adjust an array of temperatures. This single scalar value is added to every temperature in the array. Using scalar broadcasting, the offset is automatically applied to each element. This makes the adjustment efficient and concise without writing explicit loops. NumPy uses broadcasting to let you add a single scalar value to every element of an array at once. For example, if you have an array of temperatures in Fahrenheit and a fixed calibration offset, you can add the offset directly to the array. NumPy automatically applies this addition to each temperature, producing a new array of adjusted values. This works efficiently because NumPy handles the elementwise operation internally without needing explicit loops. We first display the original temperatures in Fahrenheit to establish a clear baseline before making any changes. Seeing this initial array lets us compare it directly with the adjusted values that result from adding a single scalar to every element. This visual comparison helps you understand how scalar broadcasting works and how each individual temperature is affected by the addition. In short, printing the original data is an important step for interpreting the impact of the operation that follows. This code prints the adjusted temperatures in Fahrenheit to show how scalar broadcasting works. A single calibration value is added to every element in the temperature array. As a result, each original temperature increases by the same offset. This illustrates how NumPy broadcasting makes it simple and efficient to apply one scalar adjustment to an entire array at once. We create a simple two-dimensional array with NumPy to represent image brightness values using 10 and 20 in the first row and 30 and 40 in the second row. The array is defined with a floating point data type so that later calculations keep full precision. This setup lets us easily adjust and process brightness across the entire image using NumPy's array operations. To make an image brighter, we can add a constant value, such as 5, to every pixel in the image. Using NumPy, this is done by adding a single scalar value to the entire image array. NumPy's broadcasting feature automatically applies this scalar across all dimensions of the array. As a result, each pixel's intensity increases by 5, and the whole image appears brighter. To increase the brightness of an image stored as a two-dimensional array, we add a single scalar value to every pixel. Using NumPy, this is done through broadcasting, which automatically applies the same addition across both dimensions of the array. As a result, each pixel's value is increased by the same amount, making the entire image brighter. We begin by printing the original pixel values of the image stored in a two-dimensional array to establish a baseline for comparison. This output shows the initial brightness levels across the image before any changes are made. Having this starting view is important because it lets us clearly see how later operations, such as applying scalar broadcasting, alter the image data. In other words, it helps us understand the effect of our modifications by comparing the adjusted image to its original state. We now display the brightened image pixels to demonstrate how scalar broadcasting works across two dimensions. By adding a single scalar value to every element in a two-dimensional array, each pixel's intensity increases by the same amount. This operation effectively makes the entire image brighter while preserving the relative differences between pixels. The printed pixel values clearly show this uniform increase in brightness across the image. This script shows how scalar broadcasting works in NumPy by applying a single value across entire arrays. It first creates a one-dimensional array of daily temperatures in Fahrenheit and adds a calibration offset, letting NumPy automatically adjust every temperature at once. It then uses a two-dimensional array to represent image pixel brightness and adds a scalar value to increase brightness uniformly across all pixels. By printing the original and modified values in both cases, the script illustrates how broadcasting efficiently applies a scalar to every element, even in multiple dimensions, without manual loops. Array aggregation basics. Core statistical aggregates. When working with numerical data in arrays, it is useful to summarize the data using key statistics, such as the total sum, the arithmetic mean, and the smallest and largest values. These measures quickly answer questions about the overall total, the typical value, and the extremes in the dataset. For example, in daily sales or temperature readings, the sum, mean, minimum, and maximum give a fast overview of performance or conditions without checking every individual value. In this way, simple aggregates turn raw arrays of numbers into meaningful insights efficiently. Statistical aggregates like sum, mean, minimum, and maximum operate over all elements of an array, whether it is one-dimensional or multi-dimensional. In a one-dimensional array, such as a list of delivery distances, the sum simply adds all values together. In a two-dimensional array, such as an image or a table of exam scores, these operations still produce a single summary number. The mean can describe overall brightness in an image or the average score in a class, while the minimum and maximum show the range of values, helping you quickly see extremes and the spread of the data. Core statistical aggregates like sum, mean, minimum, and maximum can be tailored to the structure of your data by choosing how they move across arrays. Instead of only computing a single overall value, you can, for example, average scores per student across exams or per exam across students. In time series data, you can also compute daily, weekly, or monthly averages from hourly measurements to reveal different patterns. Learning to apply these aggregates on arrays of different shapes is a key step toward more advanced analysis and building complex, data-driven models. Python code, core statistical aggregates. In this lesson, we use simple daily sales data to demonstrate core array aggregate operations. We focus on a one-dimensional array and show how to compute the total sales using the sum, the average sales using the mean, and also find the minimum and maximum sales values. We then compare these whole array aggregates with summaries calculated separately for each row and for each column. This highlights the difference between treating the data as a single collection and analyzing it by rows or by columns. We begin by using the NumPy library, a key tool in Python for numerical work. NumPy supports large, multi-dimensional arrays and matrices and offers many mathematical functions to work with them. In this script, it is used to manage sales data and perform statistical calculations efficiently. We use a NumPy array to store daily sales data for 1 week, with each position in the array representing the dollar sales for a specific day. Organizing the data this way makes it easy to work with the entire week at once. Using NumPy's built-in tools, we can quickly compute useful statistics on the sales, such as the total for the week or the average daily sales. We use the sum function from the numerical library to add all the daily values in the week sales array. This calculation gives us the total revenue generated over the entire week. It is a simple and efficient way to combine a series of numbers into one overall total when you need a single cumulative value. To find the average daily sales for the week, we apply the mean function from NumPy to the array of weekly sales data. This function adds up all the daily sales values and divides by the number of days. The result is a single number that represents the typical amount of sales per day over that week. To find the smallest daily sales in a week, you can use the NumPy minimum function on the weekly sales array, which scans all values and returns the lowest one. This value represents the minimum sales for a single day. To find the largest daily sales, you use the NumPy maximum function on the same array, which returns the highest value. Together, these results show the range of daily sales across the week. We begin by printing a short message to explain that we are about to show the total, average, minimum, and maximum sales for the week. Then we display the actual values for total weekly sales, average daily sales, lowest daily sales, and highest daily sales. These numbers were calculated earlier using numerical functions that compute the sum, mean, minimum, and maximum. Together, they give a quick statistical summary of the weekly sales data. We use a two-dimensional array to store sales data for 2 weeks, with each row representing 7 days. The first row holds the original weekly sales. The second row is created by multiplying each day's sales by 1.1 to model a 10% increase in the second week. This structure makes it easy to compare sales for each day across the 2 weeks and perform calculations on both weeks at once. To find the overall sales for both weeks, we use the sum function from the numerical library on the two-dimensional sales array, which adds all daily sales across the 2 weeks into one total value. We then use the mean function on the same array to calculate the average sales per day over the entire period. This gives a single number that represents the typical daily sales across all days in both weeks. To find the average sales for each day across 2 weeks, we apply the NumPy mean function to the two-dimensional sales array and set it to work along the first axis. This tells the function to average values column by column, so each column's result represents the average sales for that day over both weeks. Using this approach, we can quickly see how each day performs on average during the 2-week period. We begin by printing a short message to signal that we are about to show the overall sum and mean for the 2-week sales data, which prepares the listener for the summary that follows. Then, we display the previously calculated overall sum and overall mean values. Together, these numbers give a concise overview of total sales and the average sales per day across both weeks, providing a clear, high-level picture of sales performance over the entire 2-week period. The code first prints a message explaining that it will show the average sales for each day across the weeks. It then displays these daily averages, which were already calculated using a numerical library's mean function. This function was applied along the first dimension of a two-dimensional sales array. As a result, the output gives the average sales for each day, combining data from both weeks. This script uses NumPy to compute basic statistical summaries for daily sales data. It first calculates the total, average, minimum, and maximum sales for a single week to show overall performance. Then it models a second week where each day's sales are increased by 10% and combines both weeks into a two-dimensional array. From this, it computes the total and average sales across the 2 weeks, as well as the average sales for each day to reveal both overall trends and day-by-day consistency. All of these results are printed to illustrate how these aggregates describe sales patterns. Finding extrema indices. When working with numerical arrays, it is important to know where the minimum and maximum values occur, not just what those values are. Functions that return the positions of these extreme values give you the indices where they appear. In a one-dimensional array, this might identify the day with the lowest temperature or the product with the highest price. In multi-dimensional arrays, such as matrices, it tells you the row and column of a value, like the pixel with the highest intensity. This ability to locate positions helps connect numerical results to meaningful real-world contexts. Finding the indices of maximum or minimum values in an array becomes powerful when you think in terms of axes. In a two-dimensional array of exam scores, scanning each row for the column index of the highest value tells you which test each student did best on. Scanning each column for the row index of the highest value tells you which student scored highest on each test. The same idea works for minima. such as identifying the weakest performance. By interpreting these indices within the array's structure, you can answer questions like which day was hottest, when a stock price was lowest, or when a sensor reading peaked. When working with extrema indices, you must understand how they relate to the original data layout. If several elements share the same maximum or minimum value, the index usually refers to the first one in the array's order, often scanned row by row. Reshaping an array can change the linear index of an extreme value without changing the value itself, because the coordinate mapping changes. To avoid misinterpretation, always connect indices back to the original array or its metadata so you can state clearly which real-world item, such as a particular patient or time interval, the extreme value belongs to. Python code, finding extrema indices. This section explains how to find the positions of maximum and minimum values in simple NumPy arrays. You learn to use functions that return the index of the largest value, called argmax, and the index of the smallest value, called argmin, for both one-dimensional and two-dimensional data. It also shows how to interpret these indices by mapping them back to meaningful labels, such as which day of the week or which student corresponds to each extreme value. The goal is to connect raw array positions to real-world categories, so the results are easy to understand. In this script, we use the NumPy library, a key tool in Python for numerical computing. NumPy lets us work efficiently with large multidimensional arrays and matrices. It also provides many mathematical functions that operate directly on these arrays. Here, we rely on NumPy to manage data arrays and quickly find the positions of maximum and minimum values, which is especially useful when analyzing information such as temperatures or test scores. We use a NumPy array to store daily high temperatures in Fahrenheit as a simple one-dimensional list of numbers. Each entry in the array represents the high temperature for one day. By putting the values directly into this array, we can easily apply numerical operations to the whole set, such as finding the maximum or minimum temperature. This makes it convenient to analyze and compare temperature data across multiple days. We use a NumPy function called argmax to find the index of the largest value in a temperature array. It scans through all the values and returns the position of the highest temperature. This allows us to quickly identify which day in the dataset had the highest recorded temperature. To locate the day with the lowest temperature in an array of daily highs, you can use the argmin function from NumPy. This function searches through the array and returns the index of the smallest value. By saving this index, you can easily identify and reference the position of the minimum temperature in the dataset. We begin by printing the array of daily high temperatures in Fahrenheit to see the data we are analyzing. Then, we display the maximum temperature and its position in the array, using the index found by the NumPy argmax function, which tells us which day was the hottest. In the same way, we print the minimum temperature and its position using the index from the NumPy argmin function to find the coldest day. This links the numerical indices in the array back to meaningful information about specific days. We can use a two-dimensional NumPy array to store student test scores, where each row represents a student and each column represents a test. This structure organizes the data so that scores are easy to manage. With this setup, NumPy's array operations let us quickly analyze performance by individual student or by specific test. To find which test each student did best on, we use the argmax function from the NumPy library. We tell it to work across each row so it looks at one student's scores at a time. For every student, it returns the position of the highest score in that row. This index tells us which test was their best performance. To find which students scored highest on each test, we use the argmax function from NumPy with the axis set to 0. This tells NumPy to look at each column separately, where each column represents a test. For every test, it finds the position of the student who achieved the highest score. The output is an array in which each entry is the index of the top-performing student for a particular test. We begin by printing a short message to introduce the scores matrix, which shows each student's test scores. Then, we display the matrix itself so we can see the data and its structure. Next, we print the index of the best test for each student, using a function that finds the position of the highest score in each row. Finally, we print the index of the best student for each test, using the same idea along the columns to identify which student scored highest on each test. This script shows how to use NumPy's functions for finding the positions of maximum and minimum values in arrays. It first works with a one-dimensional array of daily high temperatures, locating the index of the highest and lowest temperatures and printing those values with their positions. It then applies the same idea to a two-dimensional array of student test scores, finding each student's best test by looking across their scores and identifying the top student for each test by looking down the scores. Overall, it demonstrates how these index-finding functions help extract useful insights from numerical data. Understanding axis reductions. When working with multi-dimensional arrays, you can choose to aggregate values along specific axes instead of collapsing everything into a single number. For example, in a sales spreadsheet where rows represent days and columns represent product categories, summing across each row gives daily totals, while summing down each column gives category totals. This idea, called axis reduction, lets you preserve the overall structure of the data while focusing on the dimension you want to summarize, whether that is rows, columns, or deeper layers in the array. When working with three-dimensional data, such as hourly temperatures for multiple cities over many days, the axis you choose for averaging changes what you learn from the data. Averaging along the hour axis gives average daily temperatures for each city and day, preserving the city and day structure. Averaging across the city axis instead shows regional trends by giving average values for each day and hour across all cities. These different results highlight how important axis selection is in data analysis. Axis reduction is about choosing the direction in which you combine data so your results answer the right question. For example, you might total energy use per household over a month, or average exam scores per student across subjects. In each case, you decide which dimension to reduce, such as time or subject, to match the question you are asking. Aligning the axis of reduction with your goal keeps the data structure meaningful while still extracting useful summaries. Python code, understanding axis reductions. This section shows how to use axis-based reductions on small NumPy arrays to better understand how these operations work. By computing sums along rows and columns, you can see how some of the original array structure is preserved in the results. The choice of axis is then connected to simple daily sales style questions, such as summing across days or across products, to illustrate how different axis choices answer different practical questions. We begin by importing the NumPy library, which is a key tool for working with arrays and performing fast numerical calculations. Using NumPy allows the script to handle array operations efficiently. This import step sets up everything needed for the array manipulations and computations that come next in the code. We begin by creating a small sales table using a two-dimensional NumPy array, where each row represents a day and each column represents a product. Every entry in this array stores the sales amount in dollars. The values are defined as floating point numbers to maintain precision for any calculations we perform later. We begin by printing the sales table so we can see how it is organized. This table is a two-dimensional array, where each row represents a different day and each column represents a different product. Viewing the table makes the layout of the data clear and shows how daily sales are arranged across products. This visual understanding provides important context for any further analysis or operations we perform on the array. To find the total sales for each day, we add up the sales of all products for that day, which means summing across the rows of the sales table. This calculation produces a one-dimensional list where each value represents the total sales for a specific day. We then print these daily totals to show how much was sold on each day across all products. To find the total sales for each product across all days, we add up the sales values down each column of the table. This means we sum along the row dimension so that each product ends up with a single total value. These totals are then stored and printed, showing the overall sales per product. This summary helps reveal which products generated the most revenue over the period. We use a three-dimensional array in NumPy to represent temperatures in Fahrenheit, organized by city, day, and hour. This structure lets us store hourly temperature readings for multiple cities over several days in a single organized dataset. By initializing the array with specific temperature values, we get a clear example of how multi-dimensional arrays can be used to manage and access complex weather data. We calculate the mean temperature by averaging the hourly readings for each city and each day along the hours dimension. This produces a two-dimensional array where each entry is the average daily temperature for one city on one day. We then print this array to see the mean temperatures per city per day, which helps us compare and understand daily temperature trends across different cities. To analyze the temperature data, we calculate the average temperature over all days for each city and each hour. We do this by applying a mean operation across the day dimension, which keeps the city and hour structure intact. The result is a new set of values that gives the mean temperature for every city at every hour. When we print these values, we can see how the typical temperature changes by hour across different cities. This material explains how axis-based reductions work in NumPy arrays using simple data examples. In a two-dimensional sales table, summing across columns gives total sales for each day, while summing across rows gives total sales for each product. In a three-dimensional temperature array, taking the mean over the hour axis gives average temperatures for each city on each day, and taking the mean over the day axis gives average temperatures for each city at each hour. By choosing different axes for operations like sum or mean, you control which dimensions are combined and which are preserved, allowing you to answer specific questions such as daily totals or average values over time. Linear Algebra Essentials. Dot products in NumPy. The dot product is an operation that combines two vectors into a single number that measures how aligned they are. It is large and positive when the vectors point in similar directions, negative when they point in opposite directions, and close to zero when they are orthogonal. This idea connects numerical arrays to geometric and statistical insights and appears in tasks like comparing user preferences, computing physical work, or summing weighted features in machine learning. NumPy provides efficient tools to compute dot products for arrays of many sizes, from simple vectors to large, high-dimensional data. Two-dimensional arrays can be viewed as matrices, where matrix multiplication is built from dot products. Each entry in the product matrix is the dot product of a row from the first matrix and a column from the second. In practical terms, multiplying a sales matrix by a commission matrix can produce total commissions for each product and region. In data science, multiplying a feature matrix by a weight vector gives predictions, where each prediction is a dot product of features and weights. Libraries like NumPy implement these operations efficiently, making them fast and scalable for large datasets. Dot products in NumPy are a core tool for advanced linear algebra and for working with complex data. Geometrically, they relate to the cosine of the angle between vectors, which makes them useful for measuring similarity in high-dimensional spaces, such as document embeddings. In statistics, they support projections and quadratic forms that help quantify variance. And in engineering, they form the basis of operations like correlation by repeatedly sliding signals and taking dot products. Recognizing many tasks as repeated dot products shows why NumPy's efficient implementation is so important and lets you avoid slow manual loops. Python code. Dot products in NumPy. We want to show simple examples of NumPy dot products using clear numbers. Then, compare the result you would get by manually multiplying and adding the vector components with the result from the NumPy dot function. This helps confirm that the function is doing the same computation you would do by hand. We also connect the dot product to the angle between short vectors, explaining that a larger dot product usually means the vectors point in a more similar direction. In this way, learners see both how to compute dot products and how they relate to similarity between vectors. In this script, we use NumPy, a Python library designed for efficient numerical computing with arrays and matrices. NumPy provides tools to work with these data structures and includes many built-in mathematical functions. Here, it is used to compute dot products and vector magnitudes, which are key for analyzing vector relationships. It also helps perform matrix multiplications quickly and efficiently. We begin by defining two three-dimensional vectors using a numerical computing library. and we interpret these vectors as forces measured in pounds force. The first force vector has components 3, 4, and 0, and the second has components 4, 0, and 5. We will use these two force vectors to carry out operations such as the dot product and to discuss what these operations mean geometrically. To compute the dot product of two vectors by hand, multiply each pair of corresponding elements from the two vectors, then add those products together. You start with the first elements of each vector, multiply them, and note the result. Repeat this for the second elements, then for the third elements, and so on if the vectors are longer. Finally, sum all these individual products. That total is the dot product of the two vectors. We use the NumPy dot function to compute the dot product of two force vectors. This operation multiplies corresponding elements of the vectors and then adds those products together. Using the NumPy implementation is much faster and more reliable than doing this calculation manually. It is especially helpful when working with large datasets or complex vector operations, where both accuracy and performance are important. We first display the result of the dot product computed manually, then display the result from NumPy's dot function. Comparing these two values shows that they match. This confirms that NumPy's implementation is accurate. It also highlights how convenient it is to use NumPy for dot product calculations instead of doing them by hand. We use a NumPy linear algebra norm function to find the magnitudes of two vectors. First, we calculate the magnitude of the vector representing force A, which gives its length in three-dimensional space. Then, we calculate the magnitude of the vector representing force B in the same way. These magnitudes are important because they are used in later steps, such as computing the cosine of the angle between the vectors to understand how their directions relate. To find the cosine of the angle between two vectors, you compute their dot product and then divide by the product of their magnitudes. This value tells you how closely the vectors are aligned. A cosine value close to 1 means the vectors point in nearly the same direction. We first report the magnitude of force A, rounding the value to 3 decimal places for clarity. We then do the same for force B, so both magnitudes use the same level of precision. Finally, we output the cosine of the angle between the two vectors, also rounded to 3 decimal places. This cosine value represents the cosine similarity and indicates how closely aligned the directions of the two forces are. We create a two-dimensional array of features with 2 rows and 2 columns, where the first row contains the values 1 and 2, and the second row contains 3 and 4. We also define a one-dimensional array of weights with 2 values, 10 and -1. This setup is commonly used for matrix multiplication, where each feature row is multiplied by the weight array. The result of this multiplication is a set of predictions based on the given features and weights. We compute predictions by taking the dot product of each feature row with the weights vector. This means we multiply each feature value by its corresponding weight and then add up these products. The result is a single prediction value for each row of features. This process applies a linear transformation to the inputs and is commonly used in machine learning models, where the feature rows are inputs and the weights represent the model parameters. This code computes and prints predictions by taking the dot product of each row in a feature matrix with a single weight vector. In other words, it multiplies each set of input features by the same weights to produce one prediction per row. By doing all these dot products in a batch, it shows how multiple predictions can be calculated efficiently in a single operation. This script shows how to compute dot products and use them to understand vector relationships and make simple predictions. It begins with two three-dimensional force vectors, calculates their dot product manually, and then confirms the same result using a numerical library. It then finds the magnitude of each vector and uses these values with the dot product to compute the cosine of the angle between them, illustrating cosine similarity and how it reflects their orientation. Finally, the script performs a small matrix multiplication by taking dot products between each row of a feature matrix and a weight vector, producing a set of predictions similar to those used in linear regression. Transpose with T. Transposing an array is important in numerical computing because it lets you switch how data is oriented without changing the underlying values. In NumPy, this is efficient since the transpose is just a new view of the same data, not a copy. For example, you can flip a sales table so that products and months swap roles, which can make analysis or visualization easier. Transposes are also fundamental in linear algebra, where they help align vectors and matrices correctly for operations such as dot products and matrix multiplication. Transposing vectors and matrices is important for making their shapes align correctly in linear algebra tasks. A one-dimensional list of features can be treated as either a row or a column, and taking the transpose of its two-dimensional form lets you switch between these views as needed, such as when multiplying a matrix of observations by a parameter vector in machine learning. In recommendation systems, user ratings are often stored in a matrix with users as rows and items as columns, and transposing this matrix lets you instead treat items as rows and users as columns, which can simplify computing item similarities. The key idea is that the transpose does not change the data values, only how they are oriented and matched with other arrays in your calculations. Transposing becomes especially powerful with higher dimensional data, such as images with height, width, and color channels, because it lets you permute axes to match the needs of different algorithms or libraries. In time series analysis, transposing a two-dimensional array of sensor readings lets you switch between viewing data by time or by sensor, which can simplify correlation calculations and model inputs. By mastering transposition, you gain the flexibility to reshape arrays so that complex linear algebra operations become more intuitive and efficient. Python code. Transpose with T. Use the basic transpose feature in NumPy, accessed through the T attribute, to flip a matrix so that its rows become columns and its columns become rows. After transposing, compare the original matrix to the transposed one to clearly see how the positions of elements change. Also, relate this to matrix shapes in a simple dot product example, showing how the dimensions before and after transpose affect whether the dot product is valid. We begin by importing the numerical computing library that specializes in working with arrays. This library is essential because it lets us handle large collections of numbers efficiently. It also provides the core tools we need for matrix operations and other numerical calculations used throughout the script. We use a two-dimensional array from NumPy to store sales data measured in inches per month. In this array, each row represents a different product, and each column represents a different month. Organizing the data this way makes it easier to manage and analyze sales across multiple products and time periods. We begin by printing a short message that explains how the data is organized, with products as rows and months as columns. Then we display the array itself, which shows how many inches were sold for each product in each month. After that, we print the shape of the array to confirm its dimensions, telling us exactly how many products and how many months are included. These steps make sure we clearly understand the layout of the data before performing any further transformations. We use the transpose attribute to swap the rows and columns of the data array, effectively flipping its dimensions. This changes the layout so that months become the rows and products become the columns. After transposing, we print the rearranged data and then display the new shape of the array to confirm that its dimensions have been updated. We begin by setting up an array of prices per inch for each product, arranged so it lines up correctly for matrix multiplication. We then multiply the transposed sales data by this price array to compute revenue in dollars. This multiplication combines the monthly sales for each product with its price, producing a new array of total revenue for each month. Finally, we output this monthly revenue to clearly show the financial results based on the given sales and pricing data. This example shows how the transpose feature in NumPy can be used to work with a two-dimensional array more effectively. The array starts out with products as rows and months as columns, representing inches sold. When the array is transposed, rows and columns are flipped so that months become rows and products become columns. This new orientation makes it possible to take a dot product with a separate array of prices per inch. The result is an array of revenue values in dollars for each month, demonstrating how transposing helps align dimensions for operations like dot products. Vector norm basics. In numerical computing, a vector norm is a single number that measures the size or length of a vector, or how far it is from the origin. It compresses all the vector's components into one value, which is especially helpful in high dimensions where you cannot easily visualize the data. This magnitude can represent quantities like the intensity of a signal or the strength of a force. Norms are widely used to compare vectors, set thresholds, and carry out further calculations efficiently. Norms provide a consistent way to measure and compare the size of vectors. In machine learning, the norm of a feature vector indicates how large a data point is, which can influence algorithm decisions. In engineering, norms capture quantities like speed or force strength without regard to direction. By turning complex vector data into a single magnitude, norms make it easier to detect outliers, track convergence, and set meaningful thresholds for alerts or decisions. In numerical libraries, norms are built from basic linear algebra operations, such as taking the dot product of a vector with itself to measure its magnitude. For matrices, norms describe the overall size or strength of the transformation they represent. These measures are important in practical areas like image processing and control systems, where they help quantify differences and monitor stability. Understanding norms in this way helps you use NumPy's tools more effectively and interpret their outputs as meaningful, real-world measures. Python code. Vector norm basics. Vector norms give a single number that measures the overall size or magnitude of a vector. You can compute this distance manually using the coordinates, or you can use a built-in norm function from a numerical library to get the same result more efficiently. Norms are closely related to dot products, which provide a geometric way to understand how vector length and the angle between vectors are connected. Together, these ideas link algebraic calculations with geometric intuition about vectors in space. We begin by using the NumPy library in Python, which is designed for fast and efficient numerical computations. NumPy offers many mathematical tools that make it easier to work with vectors. With this library, we can quickly perform operations such as finding vector norms and computing dot products. Throughout our work with vectors, NumPy will be the main tool that handles these calculations. We create a two-dimensional vector using NumPy to represent a displacement in feet, where the first component is 3 feet and the second component is 4 feet. This simple example is commonly used in vector math because these components form a right triangle. It provides a clear way to connect vector operations with geometric ideas, such as using the Pythagorean theorem to relate the components to the overall length of the displacement. To compute the norm of a two-dimensional vector manually, we use the distance formula. We square each component of the vector, add these squares together, and then take the square root of that sum. For a vector with components 3 and 4, we square 3, square 4, add the results, and then take the square root. This final value is the magnitude or norm of the vector. We use NumPy's linear algebra norm function to calculate the magnitude of a vector. This function gives the vector's length, which is the same as its Euclidean norm, by taking the square root of the sum of the squares of its components. Using this built-in function is concise and takes advantage of NumPy's optimized performance for numerical calculations. We first show the components of the vector in feet to visualize its direction and size. Then, we compute its length manually using the distance formula. Next, we calculate the length again using the linear algebra norm function from NumPy, which is a convenient built-in tool. Comparing the two results confirms that both methods give the same vector length, validating the accuracy of our calculations. To connect vector norms with the dot product, we take the dot product of a vector with itself. This means we multiply each component by itself and add the results. The outcome is a single number that equals the squared length or squared magnitude of the vector. Taking the square root of this value gives the vector's magnitude, which is how norms are defined. To find a vector's magnitude using the dot product, you take the dot product of the vector with itself, which gives the sum of the squares of its components. Then you take the square root of this result. This process recovers the vector's length and shows how the dot product is directly related to the vector norm. We first compute the dot product of a vector with itself, which gives the squared magnitude of that vector and is central to understanding vector norms. Then we take the square root of this value to obtain the vector's actual magnitude or norm. This process shows how the dot product directly leads to the norm and illustrates the connection between these two concepts. This script shows 3 equivalent ways to find the magnitude of a 2-dimensional vector. It first computes the norm manually using the Pythagorean theorem by taking the square root of the sum of the squares of the components. It then uses a linear algebra norm function from a numerical library to get the same result. Next, it calculates the dot product of the vector with itself, which also equals the sum of the squares of its components, and takes the square root to obtain the magnitude again. The script prints the vector, the manually computed norm, the library-based norm, the dot product, and the norm from the dot product to confirm that all methods give the same vector length. In this lecture, you learn to apply element-wise arithmetic and universal functions to one-dimensional and multidimensional arrays. Compute aggregations such as sum, mean, min, max, and axis-wise reductions on ndarrays. And perform basic linear algebra operations including dot products, matrix multiplication, and transposition using NumPy 2.2.6. In the next module, Module 2, we will go over indexing and views. Thank you for your attention. See you all in the next lecture.